Welcome to the deep dive. Today we're jumping into something pretty fundamental, maybe a bit of a shortcut actually, right into the core of how modern physics describes things.
We're looking at a really key chapter from the Feynman Lectures on Physics, Vol.2. It's all about the differential calculus of vector fields.
Yeah, and it feels like a shift, doesn't it?
Yeah.
Usually you start physics with, simple experiments, two charges pushing each other, and build up the laws.
Exactly. But this chapter, it kind of flips that. Feynman says, look, here are the complete laws, like Maxwell's equations, right up front. But they're in this advanced mathematical language, differential equation.
Right, so that's the mission today, isn't it? We're not deriving the laws from scratch. We're learning the language needed to even read those fundamental laws. It's about getting the physics inside the math.
Precisely. If you really want to grasp electricity, magnetism, gravity, the deep stuff, you need more than basic algebra. You need this vocabulary of field physics.
So we're unpacking the tools, scalar fields, vector fields, and then these key operators that describe how things change in space.
That's the plan, learning the vocabulary, essentially.
Okay, so let's start with the backdrop, the canvas for all this. Fields. The simpler one first, scalar fields. What are we talking about there?
Right. A scalar field is, well, pretty straightforward conceptually. It just means assigning a single number, a scalar value, to every single point in space. Just magnitude, no direction involved.
Like temperature.
Temperature is the perfect example. Tx, y, z, towing, you pick any coordinate x, y, z in a room, and there's a specific temperature value right there. That's it. A number everywhere.
And the book mentions visualizing these with isothermal surfaces, so like surfaces where the temperature is constant.
Exactly. Imagine these nested surfaces, maybe complex shapes, but everywhere on one particular surface, the temperature is, say, exactly 20 degrees Celsius. On another surface, inside or outside that, it's 21 degrees.
Ah, okay. Like contour lines on a map showing elevation, but in 3D showing temperature. Got it.
That's a great way to think about it. Okay, so that's scalars. Now, the next level up, vector fields. These are, well, richer, more information packed in.
Because now we have direction too, right? Not just a number.
Precisely. A vector field assigns a vector, something with both magnitude and direction, to every point in space.
The text brings up heat flow. The vector math via PA. How does that work as an example?
Okay, so think about heat moving through, say, a metal block. At any point inside that block, the heat isn't just present, it's flowing. The vector math BFE tells you two things. Its magnitude tells you how much energy is flowing past that point per second per unit area.
Okay, the intensity of the flow.
Right, and its direction. That tells you exactly which way the heat is moving at that specific spot.
So it's like mapping out wind patterns, maybe? Velocity has speed and direction at every point.
Perfect analogy. Or water flowing in a river. That's a vector field. The book also has that nice rotating disk example. The velocity of each atom depends on where it is on the disk. Both speed and direction change.
Okay, so we have these fields, scalar and vector, describing quantities everywhere in space. But the crucial thing is that these quantities usually change from place to place.
Exactly. The temperature isn't uniform. The heat flow isn't the same everywhere.
So how do we describe that change mathematically? If I take a little step, how much does the temperature change? That seems like the fundamental question.
And that brings us straight to our first really big tool, the gradient. Specifically, the gradient of a scalar field, like temperature 2.
Symbolized as a nabla T, that triangle symbol. Nabla, del.
Yep, del or nabla T sto. And the text gives a really elegant definition. It says if you take a tiny step, represented by a small vector delta math BF
Like moving a tiny bit in some direction.
then the small change you see in the temperature, delta T sto, is just the dot product of this gradient vector, nabla T dot, your step vector, delta math BF So delta T and nabla T CF
Okay, so the gradient is a vector itself.
Yes, that's key. The gradient of a scalar field is a vector field, and its meaning is incredibly powerful.
Which is?
That vector, nabla tau, at any point, points in the direction where the temperature is increasing the fastest. It points straight uphill on the temperature landscape, you could say.
Ah, okay. The direction of maximum increase.
Exactly. And the magnitude, the length of that nabla tau vector, that tells you just how steep that increase is, the rate of change in that steepest direction.
So this nabla operator, this nabla thing, it's like instructions, a command to calculate these spatial changes.
That's a perfect way to put it. It's an operator. It's not a value itself. It's a set of instructions for differentiation with respect to space. X, Y, Z, all error. It sort of wants to operate on something.
And when it operates on a scalar, like t dollars, we get the gradient vector nabla tau.
Correct. But now, what happens when this nabla operator encounters a vector field, like our heat flow math BF? This is where things get, well, even more interesting.
Because vectors have structure, direction, so you can interact with them in different ways.
Exactly. We can combine the nabla operator with the vector field math BSEA using the two kinds of vector multiplication we know, the dot product and the cross product. And these give us two fundamentally different and crucial results.
Divergence and curl.
Precisely. Let's take the dot product first. Nabla of FBF, this is called the divergence.
Okay, nabla of FBF A dot product means the answer is a scalar, just a number.
Just a number. And mathematically, you calculate it by taking the derivative of this exponent of math BFA with respect to 6 band A, plus the derivative of this component with respect to A, plus the derivative of the Z component with respect to C. It's a sum of derivatives.
Right, but what does that number mean physically?
This is really neat. The divergence at a point tells you how much the vector field is spreading out or converging right at that spot. It's like a measure of the source strength or sink strength.
The source, like something creating the flow.
Exactly. If the divergence nabla math BSA is positive, it means the field lines are originating there, flowing outwards. Think of a tap turned on underwater. Water flows out in all directions from that point. That's a source.
And if it's negative?
That's a sink. Field lines are converging, flowing into that point, like water going down a drain. If the divergence is 0, it means the flow is just passing through as much comes in as goes out. No net spreading or converging.
Okay, so divergence measures the outwardness or inwardness.
Yeah.
The source or sink density.
You got it. Source density. Now that covers spreading out, but what about sort of swirling motion, rotation?
Yeah, if the field is circulating, divergence wouldn't capture that, would it?
No, it wouldn't. For that, we need the other operation, the cross product. Nabla times math BSA. This is called the curl.
Okay, nabla times math BSA product. So the result this time is a vector.
Yes, the curl is a vector, and its direction and magnitude tell you about the rotation or circulation of the field, math BFA at that point.
How do we visualize that? The book uses a little paddle wheel.
Yeah, that's the classic picture. Imagine sticking a tiny, tiny paddle wheel into the flow field right at the point you're interested in. If the field is swirling around there, it will make the paddle wheel spin.
Okay.
The curl vector, the nabla times math BSE, points along the axis of that rotation, like using the right-hand rule. And the magnitude of the curl vector tells you how fast the little paddle wheel is spinning.
So if the curl is 0, the paddle wheel doesn't spin. The flow is smooth, no local rotation.
Exactly. If the curl is non-zero, you've got swirliness, circulation, rotation right at that point. The calculation is a bit more involved mathematically mixing derivatives like partial Hertz, partial, high partial, z more for the x component. But the physical picture is rotation.
Wow. Okay, so gradient tells you steepest slope of a scalar. Divergence tells you source sink strength of a vector. Curl tells you rotation's whirliness of a vector.
That's the core toolkit, grad, div, and curl.
And the huge payoff, the reason we're learning this specific mathematical machinery is
Maxwell's equations. The fundamental laws of electricity and magnetism. Using grad, div, and curl, you can write down these incredibly powerful laws in a remarkably compact, elegant, and universal form. 4 short equations that describe almost all of classical electromagnetism.
regardless of your coordinate system even.
Yeah.
That's the power.
That's the profound power of this vector calculus language. It captures the essence of the physics.
Okay, let's make this concrete. The chapter applies this straight away with the equation for heat flow, right? Section 2 to 6.
Yep. It shows the gradient in action in a physical law. It states that the heat flux vector, often written as math BFJ,
Which is the energy flow rate.
is proportional to the negative gradient of the temperature. So math BFJ is the gradient of temperature, pointing towards hotter regions.
Right, and kappa kappa, that's just a material property called thermal conductivity. How easily heat flows through the substance. Copper has a high kappa, styrofoam has a low kappa. But the crucial part seems to be that minus sign. Math BFJ. Why negative?
Because physics. We know heat naturally flows from hot areas to cold areas, right?
Downhill in temperature.
But the gradient, nabla T, points uphill towards increasing temperature. So for the heat flow math BFJ to point in the correct physical direction, hot to cold, it must point in the direction opposite to the gradient, hence the negative sign. It mathematically enforces the downhill flow.
That makes perfect sense. The math has to match reality.
Always. So now we've seen the first derivatives in action. The next step is looking at what happens when you apply these operators twice. Second derivatives.
Combinations of grad, div, and curl.
And there are some incredibly important combinations, particularly two that are always zero no matter what field you're dealing with. These are mathematical identities, but they reflect deep physical principles.
Okay, what's the first one?
The curl of a gradient is always zero. Nabla times equals dollars, always.
So if a vector field can be written as the gradient of some scalar function, $2. Like an electric field from static charges is the gradient of the electric potential.
Exactly. We call those potential fields or conservative fields.
Then that field cannot have any curl. It can't have any swirliness.
Never. Think about gravity. It's a gradient field, gradient of gravitational potential. You can't walk in a closed loop on a hill, a potential field, and end up at a different height than you started. There's no circulation possible. Nabla times captures that fundamental property.
Okay, that's powerful. What's the second identity?
The divergence of a curl is always zero. Nabla times math Vol.2 always.
So if a vector field math O is itself the result of some other field's curl, like how a magnetic field math O is related to the curl of a vector potential math O.
Right, or generated by circulating currents.
Then that resulting field math O cannot have any divergence. It can't have any sources or sinks.
Correct. A field that is purely curl-like must flow in closed loops. It can't originate from a point, a source, or terminate at a point, a sink. This is why magnetic field lines always form closed loops. There are no magnetic monopoles, no magnetic charges acting as sources or sinks for math BFE. This identity, nabla times math BFE, is basically the mathematical statement of no magnetic monopoles.
Wow, so these identities aren't just math tricks, they're encoding fundamental physical laws.
Absolutely. They constrain the kinds of fields that nature allows.
Now there's one more really important second derivative operator mentioned, the Laplacian.
Ah, yes, the Laplacian. Symbolized nabla 2. It comes from taking the divergence of the gradient. So nabla 2 is like nabla 2.
And when you apply it to a scalar like temperature, nabla 2 T2, what does that represent?
Mathematically, it's the sum of the second partial derivatives.
Yeah.
Frac partial 2 plus partial 2 plus frac partial 2 plus partial CM.
Okay, but physically, why is this nabla in 10 to 2s everywhere in physics? Wave equation, diffusion equation, electrostatics.
Because the Laplacian essentially measures how much the value of the field at a point deviates from the average value in its immediate neighborhood. It measures curvature, in a sense.
So if the Laplacian is 0, nabla 2t, t, what does that mean?
That usually describes a steady state or equilibrium situation. It means the field is smooth in that region, no local bumps or dips that would indicate a source or sink right there. The value at any point is exactly the average of the values around it. Think of a stretched rubber sheet. If nabla 2 of the height is 0, it's flat. It's the equation for fields in empty space or for heat flow after everything has settled down. It signifies balance.
The language of physical balance, that's neat. And finally, the chapter ties things up with a more complex identity involving a double curl.
Right, the grand finale, perhaps.
Yeah.
Nabla times, it turns out this can be broken down using the other operators. Nabla times nabla 2, not primerment.
Okay, that looks complicated, but what's the insight?
The big insight, related to something called the Helmholtz theorem, is that this shows how any reasonably well-behaved vector field, math BS, can be thought of as being made up of two fundamental parts. One part that has zero curl, which can be written as a gradient, and another part that has zero divergence, which can be written as a curl. This identity connects grad, div, curl, and the Laplacian all together, showing they form a complete system for describing vector fields.
So it confirms that these operators we've learned are truly the fundamental building blocks.
They really are.
All right, that was quite a journey through the differential calculus of vector fields. Let's recap quickly. We started with the basic concepts, scalar fields, like temperature, and vector fields, like heat flow.
Then we introduced the key operator, nabla, and saw how it acts. On scalars, it gives the gradient, nabla tot, pointing in the direction of steepest increase.
On vectors, it gives two crucial quantities, the divergence, nabla adds mathematical field measuring, or sink strength.
And the curl, nabla times math BF, measuring the rotation or swirliness.
We saw these in action with heat flow, math BF's B bond T, and learned about vital identities like nabla times and nabla times my thought BFM.
And finally, we met the Laplacian, nabla Helmholtzian, describing curvature or balance, and saw how everything interconnects.
These really are the essential tools for writing down and understanding the fundamental laws of physics, particularly electromagnetism.
Absolutely. But maybe one final important point, a word of warning from Feynman, actually.
What's that?
It's about treating that nabla operator.
Mm.
While it looks and sometimes acts like a vector, especially in formulas like divergence and curl using dot and cross products,
Yeah.
you have to be careful. It's not always safe to just treat it algebraically like a regular vector, especially when dealing with things like cross products and coordinate system changes. There are mathematical pitfalls.
So stick to the definitions.
Feynman strongly advises, especially when first learning, to rely on the component definitions, like the sum of derivatives for divergence or the specific differences of derivatives for curl, particularly in rectangular coordinates. That way, you avoid subtle errors. The symbolic math BFA and nabla times math BFA are powerful notations, but the component definitions are the bedrock.
Excellent practical advice. Precision really matters here.
Yeah.
So what does this all mean for you listening? Well, you now have the foundational language, the vocabulary, to start decoding the sophisticated equations that describe our universe, like Maxwell's equations. You can begin to see the physics inside the math.
It's the language of structure, elegance, and deep physical insight.
Thanks for diving deep with us today.